Hello everyone. Today we shall discuss about excess pressure in liquid drops. Today we'll discuss about excess pressure, excess pressure in liquid drops, excess pressure in liquid drops, bubbles or air bubbles you can say, bubbles and and this is a case of liquid drop, or you can say it as excess pressure in air bubble, excess pressure in air bubble. So we'll learn the what are the excess pressure in liquid drops, in air bubble and soap bubble and soap bubble. So we'll find the various difference between them. What is the excess pressure? How to find? For that you have to know some question, that is why drops and bubbles are spherical. First we want to learn the why. The question we want to learn that why are soaps, why are drops and bubbles, why are drops and bubbles, drops and bubbles spherical. That I am going to learn why they are drops and bubbles spherical. What keep soap bubbles stable? What keeps soap bubble stable? These answers we want to the answers of these questions we want to find out from this lesson, that is excess pressure in liquid drops, air bubble and soap bubble. Now a liquid as a liquid air interface has energy. We know that. We know that we know that a liquid air interface, a liquid air interface, a liquid air interface has energy. A liquid air interface has energy. So for a given volume, so for a given volume, so for a given volume, the surface with minimum energy, the surface with minimum energy, surface with minimum energy, the surface with minimum energy is the one with the least area, This is important. So for a given volume, the surface with minimum energy is the one with the least area. The sphere has this property. The sphere has this property. The sphere has this property. So for this reason, so for this reason, for this reason, so for this reason, the drops and bubbles are spherical. Drops and bubbles, drops and bubbles are spherical. Drops and bubbles are spherical. Another interesting here you will find another interesting consequence of surface tension is that the pressure inside a spherical drop. Another interesting another interesting consequence of surface tension. Consequence. Another interesting consequence of surface tension. Of surface tension. Another interesting consequence of surface tension is that the pressure inside a spherical drop. That the pressure inside a spherical drop. A spherical drop. So we'll find a drop here. We'll take a drop here. This is liquid drop. Inside is liquid. So we can find that the to find that the pressure inside the drop the pressure inside the drop is more than the pressure outside. So we have taken a liquid, right? So we got a liquid air interface. This is liquid and this is air. So we got a liquid air interface, right? So the pressure inside the drop is more than the pressure outside. Let the pressure inside be Pi. Let the pressure inside the drop be Pi. Inside or internal pressure is Pi, and the external pressure, external pressure be Po. What do you find that the internal pressure is greater than the external pressure? Now let us take what we are getting. We want to find, suppose this is a spherical drop, liquid drop. Suppose inside there is liquid. So we get a liquid air interface. This is liquid, this is air. Liquid air interface we are getting. And it is filled with. So here if the internal pressure is Pi, the external pressure is Po. What we find that internal pressure is always greater than the external pressure, outer pressure or external pressure. So the internal pressure is greater. So we'll find how much pressure is greater in internal. Suppose a spherical drop. Suppose Suppose a drop spherical drop of radius r of radius spherical drop of radius r is in equilibrium is in equilibrium. Suppose a spherical drop of radius r is in equilibrium, right? Suppose this is in equilibrium. If its radius is increased by del r, suppose the radius of this spherical is r, and suppose this spherical drop has increased there is excess pressure, so this radius is let the radius be r, and it increased to del r. This is del r, increase to del r, right? So what we'll get if the radius increased by del r, if the radius increased by del r, increase by del r, the extra surface energy is the extra surface energy the extra surface energy is area. Surface energy is defined as surface energy. We know that surface energy is equal to surface tension S into area. Surface tension into area is the surface energy. We previously have done that what is surface energy. So surface energy is surface tension into area. So we will find the extra surface energy is the energy of the outer spherical. What is that? That is 4 pi r plus del r whole square, r plus del r whole square minus the smaller one, that is 4 pi r square minus 4 pi r. This is the change in area into surface tension S into L A, liquid air interface, surface tension liquid air interface, right? So the extra surface energy is this one. So if we calculate this one, what we'll get? Take common, so we will find it here in this way, that it will be 4 pi, it will be a plus b whole square. We will apply the formula. So we are getting a formula r square plus del r square plus 2r del r minus 4 pi r square is La, liquid air interface. Now what we are getting here, you see that you are getting 4 pi r square, 4 pi r square plus 4 pi del r square plus 8 pi r del r minus 4 pi r square into S into L into a liquid air interface. So you see here that these will cancel out, 4 pi r square in both the cases, right? And since the del r is very small, if we square it, it will be negligible, nearly 0. So you can neglect this one also. So we are getting a value of 8 pi r del r into S La, that is liquid air interface. If the drop is in equilibrium, this energy, if the drop is in equilibrium, if the drop is in equilibrium, if the drop is in equilibrium, this energy cost is balanced. This energy cost is balanced. This energy cost is balanced by the energy gain, by the energy gain, the energy gain due to expansion, due to expansion, due to expansion under the pressure difference, 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 Pi minus Po, between the inside of the bubble and the outside, between the inside of the bubble, between the inside of the bubble, between the inside of the bubble, inside of the bubble and the outside, So what you are getting, that if the drop is in equilibrium, this energy cost is balanced by the energy gain due to expansion and the pressure difference, Pi minus Po, between the inside of the bubble and the outside. So now we'll find the work done. This is equation 1. We'll find the total work done. So here you find that the work done is the work done is W is equal to. Now what is the formula for work done? You know that work done is equal to work equal to force into displacement. And you know that pressure can be defined as force per unit area. Right? Therefore, the force can be replaced by pressure into area into D. So you're getting a point that pressure and A into D is volume. P into change in volume, that is pressure into change in volume. So you get this pressure into change in volume, right? So you get this factor. So we are getting pressure force into force equal to pressure by area, pressure equal to force by area. So in place of F we can write P into A, and A into B is D. So what can we return as pressure into change in volume del V. So here the work done is P, pressure into change in volume. So we are getting the work done as Pi minus Po into 4 pi r square del r. 4 pi r square into del r. This is the work done. So this is equation 2. So the work done will be equal to the extra surface energy. Here the work done will equal to the extra surface energy. Therefore, we can equate these two and we get a value, that is Pi minus Po into 4 pi r square, 4 pi r square del r is equal to 8 pi r del r into S liquid air interface. So we can get the value of Pi minus Po. Pi minus Po, pressure inside minus pressure outside will be equal to 4, 2 is 8, that is we are getting 2. And this pi cancel, this R, 1 R will cancel, del R cancel, then getting 2 SLA by R. This is the pressure, excess pressure in case of liquid drop. In case of liquid gas interface, in case of liquid gas interface, in case of liquid gas interface, this is liquid air or liquid gas you can say. In case of liquid gas interface, liquid gas interface, the convex side has a higher pressure than the concave side. The convex side has a higher pressure, than the concave side, higher pressure than the concave inside, So we get it here that the convex side has higher pressure than the concave side. For example, an air bubble in a liquid. For example, an air bubble in a liquid. Air bubble in a liquid means this is the bubble and this is suppose water. Air bubble in a liquid or water. I am taking a liquid as water. So this is a air bubble. What happens in this case? In this case, you will find that an air bubble would have higher pressure inside it. An air bubble in a liquid would have higher pressure inside it, That means Pi internal is greater than P outside. So here in this case also, here in case of air bubble in liquid, the excess pressure, the pressure difference will be Pi minus Po is equal to 2S. Same thing, air liquid interface by R. That is same as equation 3. Right? Now we'll deal with another thing, that is a soap bubble. What happens to soap bubble? Now this is case 2. Case 1 is liquid drop, case 2 is air bubble, and now we deal with case 3, that is a soap bubble. What happens to a soap bubble? Now suppose we are taking a soap bubble here. Case 3, excess pressure in soap bubble. Excess pressure in soap bubble. What would happen in case of excess pressure in soap bubble? Suppose this is a soap bubble, but in a soap bubble it has two surfaces. Here you can see here, though it is thin, but you have to consider it has two surfaces. Here you can see that it is a liquid air interface, liquid air, and here you find again air liquid interface, air liquid interface. So you have two surfaces, right? So in case of soap bubble, in case of soap bubble, in case of soap bubble, it has two interfaces. It has two interfaces, two interfaces, two interfaces. Applying the above argument we have for a bubble, applying the applying applying the above argument, applying the above argument, applying the above argument, we have for a bubble, we have for a bubble, for a bubble, Pi inside minus Po is equal to 4 SLA liquid air interface by R. So it will be double because there are two interfaces here. This is probably you have to blow hard, but not too hard to form a soap bubble. This is probably why. This is probably. This is probably why you have to blow hard. You have to blow hard, but not too hard, not too hard to form a soap bubble, to form a soap bubble, soap bubble. So we have explained three ways. A little extra air pressure is needed. A little extra air pressure is needed inside. Little extra air pressure is needed inside. So we have dealt with three cases. One is liquid drop, that means we get the interface. Suppose this is a liquid drop, so we are getting liquid air interface. And we have also taken a bubble in water, suppose bubble in liquid. So this is the bubble, so we are getting air liquid interface. In both the cases the pressure difference will be same, that is Pi minus Po, there is 2 SA 2 same, that is Pi minus Po is Pi minus Po is equal to 2 SLA by R in both the cases, in liquid drop and air bubble. But if you take the case of soap bubble, it will double because it has two interfaces. Here is one interface air liquid, another is liquid. It has two surfaces, this inside and there is outer layer. So in this case it is Pi minus Po, it is 4 SLA by R. Liquid air. This is air liquid or liquid air interface. Both are same. So thank you everybody for watching this video.